Today, I want to continue with our journey, our light journey over the peaks of evolutionary game theory. I remind you in the first lecture, talked about the evolution of conflict. And I tried to introduce to you the very basic mechanics of evolutionary stability analysis in simple two-player games. So after that lecture, you can justifiably tell your relatives you know game theory, right? It's not a lie. You know part of game theory. You know the essential component of it. In the second lecture, shifted focus to study cooperation, which I showed you is within a matter of perspective actually the same problem, because you can view the hawk-dove game as a cooperation problem. Introduced, we spent more time practicing the basic skills, showed you not only attracting equilibria, but repelling or unstable equilibria. In the third lecture last week, what did we do? Reciprocity, right? So it's the evolution of conflict, cooperation. I called it the evolution of relationships. Games in which you interact with the same individual more than once, and you can remember that they're the same individual. Yeah, and behave contingently. This is essential, right? If you have no memory at all, obviously it changes nothing. Yeah, if you meet the same people over and over again. But if you treat them differently because of their identity, then things can change. Today, I want to talk about what I call the evolution of families. It's a continuation of lecture 3 because we're still interested in mechanisms of assortment by which cooperators can meet cooperators at rates greater than chance. I'll say that again. We're still interested in mechanisms of assortment because at the very end of this lecture, or the very beginning of this one, or maybe both, I showed you this simple statistical assortment model where we're not saying how it happens, but if cooperators can meet one another more often than they would at chance, then there's hope in many otherwise hopeless games for cooperation to evolve and be stable. And in lecture 3, I showed you how continuing relationships and contingent behavior is one thing that can help make cooperation stable when it otherwise wouldn't be. It's effectively a mechanism of assortment. Pairs that last a long time have assorted together. Yeah, the ones that start off with defectors and give up are anti-assorted. And in today's lecture, we're going to talk about kinship or common descent as a mechanism. And this is easily the most famous mechanism of assortment to help cooperators evolve. But even so, I don't think in broader biology, any of what I'm going to talk about today is well known. It's interesting. I mean, if you talk to a behavioral ecologist, this is all the rage. Everybody's really interested in inclusive fitness and how it affects families and animals, even plants. There are lots of botanists that study social behavior. Yeah. Well, trees live near their kin. Yeah. Not all of them, but a lot of them do. And so you got to, get along with your kin. So plants have social behavior for sure. But I think, in the wider realms of population genetics, people aren't aware of this interest that those weird field biologists have in genetics. Yeah, it's this almost parallel intellectual track. So I want to give you a glimpse of all that today. And in the process, as you're getting used to, in each of these lectures, I'm trying to introduce you to some new modeling technique or give you some example of a derivation that's new. Today, it's going to look like an abrupt shift because we're going to make everything statistical. And I'm going to do a derivation for you in a framework called statistical population genetics. This will make the genetic link to evolutionary game theory more obvious. But don't worry, I'm still going to focus on the concepts, and the typeset notes have all the derivations, so you don't have to madly scribble things down. We're going to start today by focusing on a familiar game, the one we did last 2 lectures, really, this additive prisoner's dilemma, where you can cooperate or not. And if you both cooperate, you get B minus C. If you cooperate and the other one doesn't, you get minus C. If you don't cooperate and the other one does, you get B. And if neither of you cooperate, there's no change. This is the additive prisoner's dilemma that I defined last time. I'm going to start with this game again, and we're going to stick with this game for the whole lecture. This game's a little bit boring. It has no synergies, right? Non-cooperation is just being inert. Yeah, it's the most boring cooperation story and the most popular in the literature. But with the stuff I want to teach you today, show you, once you have the derivation, you can pass through it again with a different payoff matrix. Yeah, and you can think about the different games over again once I show you the framework. So it's best to study the framework with the dumbest of the game theory models. Remember in lecture 1 I said I want to convince you evolutionary game theory is incredibly stupid? Yeah, so it's best to start with the stupidest model. Everything additive and easy to work with, so you can get all of that stuff out of the way, understand the structure, the strategy of the derivation, and then you can redo derivations with any game you have in mind. And that's definitely worth doing. So you notice the homeworks I've been assigning are sometimes, I did this thing in lecture, now do it over with this other game. Yeah? This is the way you flex your brain muscle. Yeah, and you get good at stuff this way, reanalyzing other models. Our interest in this is to also come back to the assortment model that I told you before. Remember, we had this statistical assortment model where I said the probability a cooperator meets another cooperator is little r plus 1 minus r times p, where p is the frequency of cooperators in the population. You remember this? This is a couple lectures ago. So if we write the stability condition, or invasion condition rather, for cooperators in this additive prisoner's dilemma, their ability to invade a population of non-cooperators is going to be the probability they meet a cooperator given their cooperator times B minus C plus the probability they meet a non-cooperator given their cooperator times minus C. And that needs to be greater than, what is the common type getting? The common type is non-cooperate. It meets non-cooperators all the time. It gets 0. Yeah, there's a long expression that looks exactly like this one that involves zeros in it, but every term has 0. Yeah, or there's this vanishing term actually, but I'm going to skip to make this clear. So we can insert our definition in here. And this one is 1 minus r, 1 minus p, and we're imagining cooperators are rare. So we're going to make p approximately 0. So this becomes and this simplifies to something some of you will recognize. RB greater than C, which for the behavioral ecologists in the room is a famous expression called Hamilton's rule. Usually, R is interpreted as this thing you can calculate from pedigrees, from family descent diagrams, right? So if you're full siblings, the individuals in this dyad we're modeling are full siblings, then little r is a half. It's interpreted as the probability you share the altruism allele by common descent. I'll say that again. The probability you share the altruism allele by common descent. However, when I wrote this expression up top, I did not define R that way. I defined R statistically, right? So we are left with this puzzle, lots of puzzles actually, that I will impuzzle, depuzzle, today for you, unpuzzle. We need to find the assumptions which will allow us to say that this R can be calculated from a pedigree the way we think it is. Question?
I just didn't understand the word before allele.
Okay. Well, I'm not sure. Give me the context.
Okay,
There were lots of words.
It was altruistic array. You mentioned it's a probability to share the altruistic allele.
When little r is interpreted as the probability the individual share an altruistic allele by common descent.
Okay.
Yeah. Yeah, no, that's good. I say lots of things and I get lost in the stream, so you can always interrupt me and ask, but I'm not sure. I'll need locating. So thank you both for the teamwork there.
It's a Hamilton rule.
And it's Hamilton's rule, yeah. So Hamilton's rule, I used to teach an introductory evolutionary course, and I would teach Hamilton's rule, and I would do it in a way which would cause me great physical pain, because at the same time I would be teaching a version of this course where I would do to the students what I'm going to do to you today. In the undergraduate course, you just write this expression and wave your hands a lot and show pictures of monkeys. Right? But the theoretical underpinnings are never explored. Oh no, we do not discuss that. And all sorts of white lies are told. I'd like to think they're white lies because they're not malicious, but white lies are told in the pursuit of teaching, because you can't do to introductory students what I'm going to do to you today, which makes it sound terrible, but it's not. You will love it. You will bask in the glow. It'll be like seeing the aurora in the sky. Okay, it'll be wonderful. But this is a foreshadowing to say that the simple examples and definitions and justifications for Hamilton's rule are all wrong. And the real theory is way more interesting than that, and it gives us an idea of when Hamilton's rule is inaccurate, but also reassures us of its, say, qualitative validity. It tells us something very powerful about how natural selection works in family systems. But we've got a ways to go. We've got some work to do to get there. So what I'm going to do is I'm going to start with a very general definition of when natural selection increases the frequency of an allele, any allele of any kind, whether it's for social behavior or not. And that, we're going to call that step 0, I think. And that general definition is something called the price equation. So the price equation in the context of this lecture is that W bar delta P is equal to the covariance between individual fitness and individual allele frequency. I'm going to explain this at length until you are sick of it. So don't be anxious. This will be your friend or that relative that you don't like to see at parties or something by the end of the lecture. So let's start with the symbols, and there'll be more symbols, but they'll follow a theme. And so you'll be able to keep it in working memory. W's refer to fitness. This is an old population genetics convention that no one knows the origin of, but it is true. It's this theory that it comes from German Wert, but no one can validate this for me. But possible, yeah? Anyway, W with the line over it, we call this W bar, and that's an average. So W bar is the average fitness in the population, where fitness is the number of offspring, and for a simple example, with a simple life history. And delta P is the change in the frequency of an allele of interest. What allele? Whichever allele you're interested in one time step or one generation. And that is equal to, exactly equal to, well, there's an approximation coming, you know, but I'm going to, for the moment, let's pretend it's exact. It's exactly equal to the covariance between W sub I, W is fitness, I is the ID number of individual I. in the population. So each of you gets an ID number, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and that's your sub I, right? And then W sub I is your fitness, not someone else's fitness, but yours. And then PI, P sub I, is your allele frequency for the allele of interest. This is mind-bending for people for just for a moment. It's all the work in this is definitions, right? So pick some locus in your genome, and we could then pick a particular allele that occurs at this locus in the population and ask what your frequency of this allele is in your body, right? And there are 3 possible values, 0, 1/2, and 1, for most of your alleles on most of your chromosomes. Yeah. The smart-ass biologists in the crowd are thinking of sex chromosomes now, right? And yes, so for some chromosomes, the rules are different. But for most of your chromosomes, the autosomal ones, the possibilities are 0, 1/2, and 1, but it depends upon what chromosome. This system can handle all that because when we switch alleles, we can switch the context and the allowable frequencies and all of this. There are lots of interesting species like bees and wasps where males are haploid, right? Poor males. They're just like half an insect, right? So now, depending upon whether the individual is male or female, different frequencies are possible. But whatever the frequency is, P sub I is your frequency, okay? Whatever your chromosomal structure at the locus of interest, okay? This framework is used to do genetics in interesting things like plants, where the ploidy, anybody here has ever done real graduate level botany, the plant genetics is crazy. Like plant geneticists laugh at animal geneticists, right? Plant geneticists are superheroes in what they're dealing with out there, right? Plants are just like any tissue, anytime, mate with any other tissue, sure. We can do that. Yeah, animals are boring. Plants are really super. So this system, plant geneticists make use of this. We're going to do something much more boring and animal focused, but this can flex and do much more fancy stuff. Do these symbols make some sense?
So it also plants try to disperse the seeds as far away from the mother plant as possible
Yes.
to avoid competition. So this is not applicable for this.
Well, we're going to do that on Wednesday. We're going to do exactly that on Wednesday, the dispersal question. Yes. Because this primes it up, exactly what happened in your brain. You see this and then you think of the spatial structure issues. So we're going to do that on Wednesday. Okay. This is definitional so far. I haven't justified this, but I'm going to do that. All right. I want to spend some time justifying this expression, but I want to give you the outline of what we're going to accomplish with it first, because when we're doing the derivation, I don't want you to feel like, well, you're in the middle of a derivation and then there's steps that are just like, sure, why not, right? It's nice to know there's a destination. Like at the end of this, we're going to do something with this expression and we're not just doing it for fun. Yeah, and so what are we going to do with this? Well, we're going to walk through 3 assumptions that are required to go from this very general expression to Hamilton's rule. We're going to transform it into Hamilton's rule one step at a time. And that'll make explicit what's required, starting with a perfectly general statement about natural selection to get to this thing. And that will hopefully tell us how we calculate R from a pedigree, or what kind of person we would need to be to calculate R from a pedigree. What would we be willing, what do we have to assume in order to do that? And the first step, let me think about the direction of this. I think the first step is that we choose additive fitness effects. You can actually do these in any order, so I have to remember what order I did in the notes. That's the trick. And I'll explain what that means when we come to it. For now, just let it sound mystical. These are fitness effects and they're additive, right? Whatever that means. Yeah. And then we're going to do some more additive stuff. Then we're going to assume additive genetics. And then finally, we're going to assume that there's no selection at the locus of interest. Which sounds bad. But trust me, it's okay. No, it's more interesting than okay. All right, that's what we're going to do. To do this, all right, how should I proceed here? Okay, let's start with definitions. So, the thing about this framework that the price equation comes out of is a framework called statistical population genetics. It's statistical because all the variables are random variables, like in probability theory. That's what the statistical is supposed to cue you to. Yeah. So they have distributions, and we have indices for all of them, and we can have standard random variable definitions. So in that sense, all of these symbols like P, the frequency of the allele of interest in the population, it has a definition. It's an expectation, right? It's the expectation over individuals. So if we could go in the population and genotype everybody, if we got the frequency of the allele of interest in their bodies, and then we average over individuals, then we have the frequency in the population, right? The frequency in the population is not a direct measurement. It's something you get by measuring individuals. Does that make sense? Yeah, and we have a definition for that. The expected value of P sub I, and that is the sum over I of what you say. And this is when it gets a little bit weird, but I will demystify it for you. And this is just definition. So the big E means expectation. You can say average. There's no mathematician in the room to complain about that. And of individual allele frequency, we sum over all individuals I, their individual allele frequency, but we weight them by this little thing n sub I. N sub I is how many chromosomes you have at this locus, to speak casually. Okay. Plant geneticists would complain about that definition. But or your ploidy. For the biologists here, remember the word ploidy? Diploid, haploid. Okay, this is your ploidy. And for most of you, it's a terrible word. But for most of you, for most of your loci, it's 2. But on sex chromosomes, it'll depend. Yeah. And again, with plants, it could be 4, 8, 16, whatever. Sky's the limit. Plants just do crazy stuff with their ploidies. Yeah. This is just a definition. There is no biology in this at all, right? It's just a definition of an average. There will be biology in a moment, I promise. And that's what motivates the whole thing. To add biology to this, so this gives us a so-called statistical definition of P. We're interested in the population dynamics of this frequency because we're tracking what is natural selection going to do to this frequency. So we want to compare P to what it is in the next generation. Yeah, question?
So the ploidy is just the small n, or is it fraction?
It's the ploidy is n sub I is individual I's ploidy.
And what is the big N?
Big N is the total ploidy in the whole population. Sorry, I did not say that. Yeah, capital N is the total ploidy. You can think of it as the population size of alleles. Yeah. So individuals are like these ephemeral shells for alleles, right? And the alleles are in control in this model, right? They're riding around in these big flesh cars, yeah, waiting for a chance to do some meiosis or whatever. And so this capital N is the real population size from their perspective. It gives you a way to do the averaging. Okay? All right. So our mission is to know how much this changes in one generation. So what we're going to do is write the definition of delta P, which is P prime minus P. This is a convention in a lot of applied mathematics to put a prime next to a variable. It doesn't indicate a derivative. It indicates the variable has the same definition, but its value has changed. I'll say that again. It does not indicate a derivative. Here in Leipzig, the home of calculus, we use the Leibniz notation, right? We will not be doing primes. No, like barbarians. We use it, the general use in applied mathematics, and this also applies to the derivative case, is it means the variable has the same definition, but its value has changed. So in PopGen, that means it's the frequency in the next time step. Right, so delta P is the amount that P changes in one time step, and that is by definition P prime minus P.
It's related to derivative.
What's that?
It's related to derivative.
Yes, it's related to the derivative, yes. If we squint and there's no mathematician in the room to really complain about limit theory, then you can do lots of things. And, all right, and we can write this down. We have definitions for these things. Yeah. What is P prime? And that's the first thing. Well, P prime is just this. It's the same definition, but with primes on everything. I'll say that again because it sounded vapid, but it's not. So the definition of P prime is the same definition of P, but we just put primes on everything inside of it. That's the power of the prime. It just flows right through the definitions. This will get us someplace, trust me. So in I prime, in prime, P prime sub I. Yep, minus P, and P has that definition, but I'm not going to write the whole thing. So now let's think about each of these. And then some biology will start to happen in your brain. N sub I prime remember I told you N sub I is the individual's ploidy. N sub I prime is how many alleles they contribute to the next generation, right? It's like their future ploidy, right? But this is their offspring, right? How many alleles have they, or slots for alleles have they produced into the future? And so N sub I prime, we're going to invent a symbol for this, is W sub I, N sub I. Right, this is all in the notes where it moves much more slowly, but here I have a chance to give you some concepts. So N sub I prime is N sub I W sub I. This is definitional. This defines what W sub I means, which is the fitness. Right, so there's your ploidy, and we multiply that by your fitness, and we get how much future ploidy you have contributed to the gene pool in the next time step. That's the implicit definition of fitness in this accounting system. And we divide that by, we do the same thing to capital N. N prime is the average fitness times the total ploidy. So that's like how much the population size of alleles changes in a time step. And then we still have P prime. Good? It will get exciting, trust me. Well, for me, it will be exciting. I can't promise how you'll react. But, all right, what are we going to do now? We're going to erase these steps. I should have put those over there. Okay. What we are going to do now is, this is where it gets fun. Okay, and I want to show you this. I'm going to do this derivation. As tempting as it is to skip and save time and show you something else. I think there's real value in showing you the next steps to deriving the price equation, because it's the kind, what I'm about to do is the kind of thing that happens all the time in applied math, where there's a step in the derivation which seems really non-obvious, but it's actually a standard solution strategy. And so I want to show it to you. It's not the kind of thing you would normally think to do because you're a sane, well-adjusted adult person. But if you do applied math long enough, it lets you see into this, well, I mean, they're just a toolbox of things you try. And one of the approaches is if there's an expression in what you're working with that resembles part of some other expression you understand, then you can just add the rest of that expression so that you can make it into the thing you understand. I'll say this again. There's part of the expression that resembles something you understand, but it's missing some term, say. It's not complete. Then just add what's missing. Now, I know you're thinking, but you can't just add stuff, Richard. Oh, yes, you can. And we will. And why would you do that? Because then, once you've added what's missing, you can factor it all together as that thing you understand, and you can interpret it. And yes, there'll be other stuff in the expression. And that's going to be interesting, too, because it'll be this emergent, like, aha, that was there all along sort of thing. And I'm about to do this standard kind of strategy for you, and it happens all the time in applied math. Now, why can we just add something? We can add anything as long as we subtract it at the same time. And this is why a healthy adult human being would not do this, right? Because you would not say to yourself, aha, what I need to do with this expression is add and simultaneously subtract some value to it. But that's exactly what we're going to do, and it will make everything better. Okay?
Basics, my teachers call that happy ending.
Is that what it's called? Yeah, I remember in high school when I first saw this derivation, I was a math team geek, you could probably guess, right? And so it just seems like madness. But then once you get it, you see it everywhere. It's just a solution strategy you do all the time. Okay, so we're going to do it for this. And we're going to do it strategically because when we see this thing, it resembles part of something that, at least if you're a person like me and you've been ruined by an adulthood of applied mathematics, you see this and you immediately think of a famous expression in statistics. And that expression is the covariance. So a covariance, variances and covariances, if you do applied stats for long, these expressions just dance in your sleep. Like you just see them in your mind all the time. So you should not have the deep familiarity with these expressions that I do. That's not healthy. But if you work with them all the time, you know that the covariance between two random variables, x and y, can be written different ways. But I'm going to write it as this. It's the expectation of random variable x times the difference between y and its mean. There's lots of ways to say this. Or it's the average product of x and y's deviation from its mean. And you can expand this and factor it and have other expressions for the covariance which make you feel different as a person. Right? There's a version where it's the difference between two products. Yeah, the average product minus the product of the averages is another version of the covariance definition. This is the one that is going to be relevant for us today.
Product you mean was fitness? I mean, it's still the expected value.
I think your question will be answered in a moment when I go forward. Yeah, there's nothing about biology here. This is just the definition. So I used x's and y's, but we're going to translate it into w's and p's in a moment. Yeah. So the relevance here is these expectations have to do with these sums, right? The sums in the expression over here are taking averages. So the link between these things, it maybe starts to seem relevant to you at this point. Okay, so what we're looking at here is we've got the average of W sub I and P sub I prime. And we've got this average of P sub I over here as well. The first thing I'm going to do, which will help you give you the flavor of it, is I'm going to multiply both sides by W bar. What that allows me to do, well, I mean, we know the answer is in this term, but that's not the reason. The reason is to get it out of the denominator here. Because as soon as I get W bar out of the denominator down here, this becomes the average product of W sub I and P sub I prime, which is starting to feel like part of a covariance. Right, so this is the strategic part of this. So once that's true, can I just do the algebra in place, right? So if we multiply the right-hand side, we multiply both sides by W bar, the W bar down here goes away, and 1 appears over here. This is this is like if you work with statistics for long, this is your covariance tingling, because this is a product of two expectations, which is a standard term in the covariance, because you're going to get the expectation of X times the expectation of Y if you multiply it out. So this starts to feel very nice. So we want to pair that up with something. What's the strategy I did in the notes? Yes, we're going to add and subtract the average product of Wi and P sub I. Okay, so we've got the sum over I of n sub I n Wi P sub I prime minus PW bar, and then I'm going to add this. Why? Because that's this, right? It's the product of X and Y, the average product of X and Y. And because the lords of algebra demand it, I must simultaneously subtract it. Trust me, this goes someplace. It's very satisfying. But this happens all the time, right? This kind of solution strategy. Now we group them in the way we want. And I'm going to start by taking these two and grouping them together. Now, make this a little clearer. This is the all right. If you left as an exercise to the student, I know it's a horrible phrase that should never be done, but that's these two expressions are equal. This is also the average product minus the product of the averages. Does that make sense? But try doing that equivalence for yourself. It's a fun algebra problem, yeah? Because you got to distribute the expectation, yeah? Do you feel the tingle?
So that's an equals
This is equals, yeah. Sorry, is there it looks like there's a line there. Yeah. Okay. And then plus Ni over N Wi Pi prime minus Ni over N Wi Pi. All right, I will pause for dramatic effect. So I have added and subtracted the same term. Yeah. Then I rearranged. I'm taking these two because I can see that they are the terms in the definition of covariance. The first one is the average product of W and P at the individual level. I'll say that again. The first one, which I moved down here. Right, if I labeled these terms, yeah, so we could call this one A and this one B, right? And then we have A and B, yeah, and C and D. Did that help?
Sorry, I still don't see much difference between A and C, for example. So I'm trying to pick up. Okay,
yeah, no, that's good. But that's good. You're working, so that's where I want you. So you're like looking at this and you're frustrated. That means you're in the right place. Yeah. So I'm going to walk you through it. I see your head. Let me walk through this, and then I'll take questions. So I've just moved them and rearranged. This is all definition. Nothing's happened yet. Now I'm going to factor these things and make them in make them in the covariances. Okay, there are going to be two covariances here. Or sorry, there's going to be one covariance and something that's almost a covariance. It's a funny expectation. So the reason I've grouped these together this way is because these two terms make together a covariance. So if X is W sub I and Y is P sub I, then this is exactly the definition of a covariance because it is the average product of fitness and allele frequency minus the product of the average allele frequency and fitness. I'll say that again. It is the average product minus the product of the averages, which is the definition of covariance. Yeah, is the average product minus the product of the averages. It matters the order you do the average, right? When do you multiply? When do you take the average? Yeah? So this is a covariance, it turns out. So I'm going to write it as a covariance. It is the covariance between Wi and P sub I. Now notice that I have made no assumptions about the distribution of fitness effects or anything like that. This is a completely general result. That is the covariance that matters, which I think is really cool. Yeah. But this defines a bunch of stuff, like the maximum change, right? The change in allele frequency is constrained in a particular way as an implication of this result as well. But there's more stuff, right? We've still got C and D. This is not a covariance. It's the average difference. We can think of it this way. It's the average over individuals, so I'm going to write it as an expectation. It's the average of Wi times P sub I prime minus P sub I. Now I'm going to erase the D so that there. Does that make it easier to see? This is the average, and I can factor the W sub I out of both, and then it's the average product of W sub I times the difference between P sub I prime and P sub I. What does P sub I prime mean? That is your allele frequency in the next generation, or the next time step, well, however we're doing the accounting. What does that mean? Well, for most life histories and most organisms, that is the same as P sub I. Because during your lifetime, your allele frequency doesn't change. Yeah? But this expression didn't have that assumption in it, and so it allows this result. And there are interesting biological cases where P sub I prime is not equal to P sub I. So there's this thing when gamete formation is not fair, there are cheater gametes. There's this phenomenon called meiotic drive, where there are certain alleles that bias their ability to get into eggs and sperm. This really happens. They're nasty little alleles. They're not nice at all. They violate the parliament of the genes, as it's called. So there's a very well-studied group of them in wild mice, right? These T alleles, they're called, in wild mice. But for most life histories, p sub I prime is equal to p sub I. Yeah. Because you got all of your DNA at one point in your life, and it is not changing frequency. Does that make sense? So this is usually 0 for most models of interest. Yeah. Because p sub I prime and p sub I are nearly the same. Christine.
I would have a really burning question. You can give a little insight in this.
Okay.
If you want to make a comment about it. Okay, so still we have a model with selection, right? You mentioned later on you talked about selection. So the selection, I guess, is in V bar. And, there's this really hot debate in biology about individual selection and group selection. And many people say it's just how much you weight the one or the other term of the price equation.
Yeah, so that's, yes. Yeah.
I mean, it's just super interesting because it's about selection, it's about the mechanics of selection. Can you relate that a little bit?
Yeah, that's I'm not going to do that today with this, but yeah, we could take this expression. So I'm not going to do this, but this is in my book, right? It turns out that the price equation is recursive, so it's self-recursive. So we can treat it as a hierarchical structure in which we have covariance within groups and covariances between groups, and this relates to this long debate in the second half of last century about group selection. And that's an interesting literature and all of that. You can't see that here yet because I haven't done the recursive embedding, right? But it's because I don't have groups in this population genetic structure to talk about. You can do that. And so and that has been historically really important in evolutionary biology because people were wrong. Famous people were just wrong. Like Maynard Smith was just wrong about group selection. And then Hamilton found Price and explained to everybody that that decomposition is possible for any model and that people have misunderstood group selection. And that is what everybody thinks now, right? It's just that different people put different spins on how important then that is for attitudes they had previously, right? So I would say there are a lot of people, particularly at British universities, who have been forced to admit they were wrong about things, but don't want it to affect what they believe about nature at all. That's my opinion. And yes, it's spicy. See, I don't think those two things can go together, right? I think, yeah.
I believe more in individual selection because finally we have the same results. Finally we get the same results, right? As everything was possible to explain by group selection, we can also explain by individual selection as soon as
if through suitable definitions of those words, that can be true, right? Yeah, it's just, then it's just a vacuous libertarian crusade, I think, is sort of what goes on in those things. But it's a question of what we think for empirically realistic population structures and life histories. What's the effect of understanding the recursive nature of the price equation? That's a different lecture, and I think it's subtle. I think it's very subtle what to conclude. So I'll beg your forgiveness for not going in that direction, but we've only got another half hour here. But there's tons to say about that. Okay, for most of you that was mysterious. What were we talking about? But no, it's this connects. Yes, this connects directly to that. It's a totally relevant question, Christine. Okay, what I want to do now I should pause. Questions? Befuddled? What's the meaning of this? I'm about to tell you the meaning of it, but I'd invite questions or indications of confusion. So we've got this expression now. This is what we've derived. And I told you before that this part of it is called the price equation. And that's true. But it always has this thing in it too. And depending upon, we have to make other assumptions to either make it go away, which is what we did here. Because if we're at the individual level, we say, P sub I prime is the same as P sub I, right? Because there's not selection happening in your body that is dynamically changing the frequencies of alleles in your body, at least for most organisms in most life histories. Yeah? Yeah, there are cancers and there is meiotic drive, and those are exceptions to this. But that's a distinction. And Christine's question was if the sub I's reference groups in the population rather than individuals, then you can reapply the same equation to get a nested version of the price equation, which has group structure and individuals inside groups, and tells you then statistically how to do the decomposition of selection, like an ANOVA. It's an analysis of variance for selection. Yeah, and that's what Christine is talking about. And then, yeah, lots of arguments among evolutionary biologists about whether that should lead us to change our minds about anything or not. Leads me to believe that, yes, lots of overconfident British biologists were wrong in the middle and second half of last century, and now we should just move on and stop talking about it. That's kind of my feeling. But people passionately have many opinions about this. So we're going to proceed the rest of the day as if this was approximately 0 and ignore it, but sometimes it's really important that it's not 0. And this is, yeah, the covariance between individual fitness and individual allele frequency. These variables, again, if you're a psychologically well-adjusted adult human, you're still a little bit nervous about them and what they mean. We're going to start modeling in a second to get us back to Hamilton's rule, and that'll help you understand those variables more because we'll make definitions for them and relate them to one another. Okay? Right now, they're just variables. They're just things you know because you're God. Yeah, but that's not how it works in real biology. Good?
Price equation?
What's that?
What's it called? Price equation?
That's named after a person. Yeah. This eccentric American engineer named Price who got interested in evolutionary biology and, yeah, kind of showed up in the UK and started working with Hamilton. And it's a very interesting life, a tragic life as well, but a really interesting life. The Wikipedia page, interesting guy, really interesting guy. Okay, so what we want to do is do some work with this expression now. And that means we're going to come back to our steps. And step 1 is additive fitness effects. And I'm going to make an assumption that I'm going to describe as additive fitness effects. I'm going to add that assumption to the price equation, simplify as much as I can, and then I'm going to go to the next step, and then the third, and after the end of the third step, we will have Hamilton's rule, and you will go forth and have a nice day. Yeah, no, and then you will understand the steps required to do this. And again, part of this is understanding what justifies Hamilton's rule and how people use it, how they shouldn't use it. And part of it is also a study in derivations and understanding applied modeling, right? You learn to model by studying other people's models. That's just how it works. I'm afraid there's no other way to do it. It's like learning a language. You just got to speak the language and listen to people. Yeah. So it's like that. What does additive fitness effects mean? It means we're going to make a definition for the fitness of an individual, W sub I. And we're going to make now, our goal is to relate individual fitness to individual allele frequency. Right, so now we're the general price equation. This allele P sub I is anything, but now we're interested in an altruism allele, an allele that makes you behave altruistically in this prisoner's dilemma in the lower left corner of the board. Yeah, that's what we're looking at. Some allele that lets you do that. So we're going to relate this to the frequency of the altruism allele. But it's going to take us a few steps to get there. What we're going to do right now is have a definition of W sub I purely in terms of this game matrix. So behaviorally, and then the price equation will relate it to the genes. So 2 steps. First, we relate it to just behavior in the game, and then the price equation will link it to genes. So we're going to make it linear, right? So the idea is if you are helped in this game, so you're some individual sub I, you're paired up in this additive prisoner's dilemma, you help or not, the other individual helps or not. Those are 2 behaviors, and I'm going to invent variables for those behaviors. Y sub I is a variable of individual I, which indicates whether or not they were helped. I don't know what Y stands for. Yes. YOLO. No one says YOLO anymore, do they? It's kind of old. But if you're helped, you get B, right? Your fitness goes up by B. And I'm going to invent a second variable, H sub I. H sub I indicates the amount of help that individual I gives. And so if they give help, they pay C. And then I'm going to add some constant to this alpha, which is just your fitness through all your other activities in life. Right? This isn't the only thing you do in life. You also feed and sleep and accumulate all kinds of other stuff. So the alpha is the average fitness, and these are marginal changes due to this social behavior, as before. The size of alpha relative to B and C is going to be important later on. So keep alpha in mind. Does this make sense? This is just the additive prisoner's dilemma written down as a function. That's all it is. It's the definition of the game. So if you wanted to redo this derivation at home tonight, because you're still so jazzed about it, using some other game matrix, this is the step, right, where you put that definition in, you change this function. Yeah.
So I got a little confused because yi is not what you receive from helps, but what you have.
Y sub I is when you are helped.
You are helped.
Yes.
And you don't report it from your own corporation again, right?
No, it's additive prisoner's dilemma, exactly. So yi is you were helped or not, H sub I is you gave help or not. Yeah, these are it's who did what in this game matrix, yeah, in the pair that individual I is in. What does this do for us? Well, we can this is a definition for WI, so we just replace WI in the price equation with this. Progress. Yeah. So W bar delta P is the covariance between WI and P sub I. So that means it's the covariance between all of this. So Y sub IB minus H sub IC plus alpha and P sub I. Totally legal. No math police to stop me. Yeah. I define WI as this thing, and then I replace WI with that thing. Yeah, totally fine. This is making assumptions about biology. Yeah, now you should feel that. There's a strong assumption because there's no synergy, right? It doesn't make any difference if we both help at the same time, for example. It doesn't reduce costs, doesn't increase benefits. So there are assumptions here. Now we can simplify this. So covariance, from the definition of covariance is a big expectation. And expectations are sums, and that means that this is commutative over addition. And so you can break up covariances just like you break up expectations and sums. That is across subtraction and addition. So this is equal to the covariance of y sub I b and p sub I minus the covariance of h sub I c and p sub I plus the covariance of alpha and p sub I. Yeah, does that feel right to you? Why is that legal? Because covariance is an expectation, and expectations are sums, and sums can be commuted across addition. Yeah, and that's how it works. If this is unfamiliar to you because, again, you've had a productive adulthood so far doing other things that are good for you, you should practice some examples with sums and convince yourself, yeah? So for example, to help motivate that, constants come out of sums. Yeah, so if something is multiplied by everything inside the sum, you can just factor it out and put it in front and get the same answer at the end. So we can do that with the constants b and c. Yeah, I just factored the b's and c's out. Yeah. And now we've got these two covariances, which I will talk about in a moment. Hang on. They have identities. These things mean something. What about this third covariance? This is the covariance between alpha and p sub I. Alpha is a constant. The covariance between a constant and anything is 0. Right? If it doesn't vary, does that feel wrong? It's right. It's absolutely wonderful. Right? If it doesn't vary, it can't covary. Yeah. If you like, you can churn through the definition and prove it to yourself. But if it doesn't vary, it can't covary. Yeah. It's like the variance of a constant. It's the same basic problem. It's not a problem. It's not its fault. It's a constant. Yeah. It just means it has no covariance with anything. Okay. So what, you ask? All right, so now we've got this thing. We've got b times the covariance between yi and pi minus c times the covariance between hi and pi. So we want to know when the altruism allele can increase in frequency, when it's rare, which means this needs to be greater than 0, right? That's our question. Yes, question.
I have a question, again, concerning the 0 at the end. What is that? Like, how is this 0 again?
Because this term on the end, the covariance between alpha and p sub I, alpha is a constant, and so this covariance has to be 0. Because constants don't have any variation, and so they have no covariation. Yeah? For the mathematical proof of that linguistic jujitsu, you should, I just erased it, but you could take the definition of a covariance and make one of the variables constant. You will find very quickly that the expectations cancel one another, and they end up being the same. Yeah. Again, in the notes, this moves at slow motion. There's a whole box on the price equation and stuff like that. So, but the conceptual thing of asking when this is greater than 0, though, that makes sense to all of you, yeah? Because we're doing ESS analysis again. And so this becomes this. B times this ratio of covariances greater than C, which I have arranged this so it has the structure of Hamilton's rule, but there's no R. We've got the B's and C's, If this were R, we'd have Hamilton's rule. So the question is, what is this? It's not R. Yeah, but we're getting there. So the top is the covariance between being helped and your allele frequency. Yeah, so if that covariance is large, that means that individuals who have altruism alleles also receive aid more than chance. Yeah, that's the covariance. If there's no relationship between your individual allele frequency, between being an altruist and receiving aid, that's 0. And then then the left is 0. So we've already learned that this has to be positive somehow for there to be any hope, right? Does that make sense? Even though we haven't done anything more. We're going to do more with it in a moment. Hang on. We'll make another assumption and do some more work. And this is the covariance between giving help and having the altruism allele. This is positive by definition. Yeah, that's the whole point. The definition of the allele is that it motivates you to provide aid. So that's positive by definition. What we need is a way for the top to be positive as well. Are you with me? Yeah? Okay. Step 2. Additive genetics. Yeah, okay. So now we're going to do to genetics what we just did to fitness, the same sort of additive violence. What this means is when we say additive genetics, we want to relate these variables y sub I and h sub I to individual genotypes. So let's start with the easy one, h sub I. We're going to choose some function that relates your genotype to the amount of aid you give, amount of helping you do. The probability, it's easier to think binary or discrete. Just think of it as the probability that you provide aid. That might be the easiest way to think of it. There are lots of functions you could choose here. Yeah, so for example, you could say if the individual has even one altruism allele, then they always provide aid. Yeah, that would be a dominant allele, right, in a diploid individual, because then the altruism allele is dominant, so that if you're a heterozygote, you still provide aid at the same rate as a homozygote. That would be one model. Yeah, but you're choosing the point is when you choose this function, you're choosing a mapping between genotype and phenotype. And we're going to make it additive, which is the easiest model. Okay, and in an additive model, there's no dominance. Just the number of alleles is proportional to the amount of aid you provide. So the simplest thing would just be something like this. A straight line. There's some little a now is the baseline amount of aid an individual provides when they have no altruism alleles. And you may be saying to yourself, but wait, if they don't have any altruism alleles, why are they providing aid? There are other loci which also affect this behavior. Yeah, and so little a is meant to sweep all that up. Okay? And this allows us to, if we squint really hard and have no geneticists within 10 meters of us, to say that this model can approximate interesting genetic structures. Yeah, but you have to feel it, like really feel it. Yeah, so does this make sense? We're going to do some work with this in a moment. Actually, let me go ahead and do the processing, and then we want to do is embed that in the covariance between y sub I and p sub I. That is now the covariance, h sub I. So now we replace h sub I with this expression, a plus k pi and pi. Again, you can break up a covariance across addition. So this is the covariance between little a and P sub I, and it's K times the covariance between Pi and Pi. And what is this? 0. Yeah, our favorite thing, right? This is also 0 because it's the covariance between a constant and something is 0. If you can't vary, you can't covary. And then we've got this thing, the covariance of P sub I and P sub I. The covariance of a variable with itself is its variance. And again, I leave it as an exercise to the student to look up the definitions of covariance and variance and verify this to yourself through a magic technique called algebra. No, I'm serious. This is like when I was a wee graduate student and I was learning all this stuff. That's how you do it. You just flex the muscles and you go through the proofs and you get good at this stuff that way. But the shortcut today is I'm just going to write it as the variance of P sub I. How much does this variable vary with itself? That is its variance. Yeah, there are all these definitions of covariance which try to relate it to variance. I think it goes the other way. I think variance is related to covariance. Yeah, it's just a kind of narcissistic covariance.
I don't really understand how that possibly can happen.
What do you mean?
I'm sorry, how does the variance of a variable vary? Okay, the covariance of the same variable.
Right. Is the average square of that variable minus the square of its expectation. And that's the definition of variance. And I've erased it, but the definition of covariance, if you make the two variables the same, then the definitions become the same. That doesn't mean you understand it, though, in a real physical sense. I understand, because it's weird. But anyway, go ahead.
It was exactly, I don't really understand how that works in real life.
In real life. This is not real life, no. You mean as in terms of the concept of variance, or in real life is a very expansive request?
Could you give me a practical example, in genetics,
Practical example.
I can just take that, obviously.
Yeah, I mean,
Just take it as it is.
it's just it's just definitional, right? It just has to do with the definition, and the covariance of a variable with itself is its variance, and its variance, as you know, is this foundational statistical measure of dispersion, and they just have these relationships.
Maybe you can define covariance and variance. Variance is the whole diversity, and covariance is how one varies with the other.
Yeah, but the relation, why it collapses like this, there's probably some deep philosophical thing that this reveals, but I don't know what that is. To me, it's just a consequence of the definitions. But there must be something more profound here that I'm missing. Yeah. No, I believe there is. I always believe there's something there, and I think it's worth thinking about these things. And but I'm sorry, I don't have anything clever to say about it. It's just true. So I got to make a little bit of progress here, though. I got 15 minutes. So. Okay, so we're halfway done here. We've converted the bottom into that. Congratulations. We're also going to convert the top. We're going to make the same assumption for y sub I. And now when I say the same assumption for y sub I, you have to watch very carefully what that means, because it's symmetric. There are two individuals in the pair. If we've assumed that h sub I equals this, then we've already assumed y sub I, because we've already imposed a mapping between genotype and phenotype, and it must apply to both individuals in the same way. And so the other individual, so y sub I is the other individual's h sub I. I'll say that again. Y sub I is the other individual's h sub I. Who's the other individual? We're going to call them J. Right? Because that's how we roll, right? So it goes IJ, yeah? So y sub I, it's the same average, the same slope, but it's the other individual's genotype that determines how much age you receive. Just like from their perspective, It's your genotype which determines how much aid they receive. Yeah, so this is required of the symmetry of what we'd call the exchangeability of I and J in the pair. Yeah, if you're taking one individual's perspective at random, then everything you write after that must be symmetric to relabeling of I and J. And that's called exchangeability in my world. Yeah. Does this make sense? Okay, so we can take this covariance between y sub I and p sub I and write it as the covariance between a plus k pj pi. The a is going to go away for the same reasons, and we're going to get k times the covariance between pj and pi. Exciting? Okay, let's put it together. So now we've got this is a lot of progress, actually. Let me try to get you amped up about this. Okay, this is where we are now. The K is in the top and the bottom, so it just goes away. Oh, isn't that great? Hardly knew you. All right, this is progress, believe it or not. We've gone from a ratio of covariances to a ratio of a covariance and a variance. But this is huge. This is really absolutely huge. Trust me. For a couple reasons. All right, the surface one, which is not at all superficial, is that we now have the top being the covariance between two genotypes. So this feels like relatedness now. Do you feel it? Yeah, the tingle? It feels like real biology there for a moment. It's just within, tantalizing, within reach. And then this is a simple quantity that's, again, related to genetics. So at least this is a ratio that's related to genotypes now. We still haven't gotten to how would we calculate this from a pedigree, but it's about genetics now. The last step we're going to need is to somehow say, relate this to R, right? We need some assumption that's going to let this be equal to R. And I'm going to inch us there. I got 10 minutes. I can do this. Okay. This thing, this expression right here, again, if you have spent your adulthood doing applied math and statistics, you see that and you recognize it immediately as another statistical quantity. You're a healthy person, you don't. Congratulations. But if you're like me, all the scars of past wars have taught you that this is a regression coefficient. This is the definition of a bivariate regression coefficient. All right. Sometimes the way this is written, right, is, well, how should I relate this? It's, the way this is usually written is a bivariate regression coefficient. It's the expectation. Actually, sorry, think about my strategy. Okay, you think of regression as a line, right? Yeah, because you're healthy people? Yeah, okay, so don't ask me what I think about it. But if you think you're a healthy person, you think about it as a line. What regression gives you is the expected value of y conditional on x. That's again, for a statistician, that's the definition of regression. And you can choose that to be a line or not. In the simplest case, it's a line, but that's what I think of as the basic definition. And at some point in your life, you learned that this is the equation for a regression. Now, this doesn't have, the typical intercepts and not, but with a bivariate regression, you can always relate it in terms of the average of the thing you're predicting. And the slope gives you the deviation from the average proportional to the difference of x from its mean value. Once upon a time you have seen this. This is not how you usually see regressions, but this is true. So we can solve for the slope. And it's the expectation of y given x minus the expectation of y over x minus the expectation of x. You believe it? I just proved it to you. That's all. That's just a fact about regression. It has nothing to do with biology or anything else. It's just for any x's and y's. But we can relate it to this, right? So this is the same thing. And so our erstwhile price equation is now b times this thing, but with the y's and x's turned into the p sub i's and p sub j's. Hang on. I planned poorly by getting to the bottom of the board there. So the expectation of p sub j conditional on p sub I minus the average of p sub I minus p sub I minus the average of p sub I. All right, this went to the bottom. I should have done more steps there of algebra. I apologize. Christine, you have your question face.
No, I was just thinking, so the covariance of a random variable is just a variance of this variable. So it's okay.
Yeah.
Also, it's exactly your question, and I was also thinking about this, and if you see it in this way, you cannot this will work. Yeah, it's if it's true, you say.
Okay. I will.
The variance of the random, the covariance of any random variable is just the variance of that variable, because I have this regression line now in mind, and how for each point it can vary, right?
Maybe I need to close the story, and then I'll be happy to talk with you two about the deep philosophical meaning of that relationship. But no, I think it's interesting. But I have 5 minutes, and I must get us to Hamilton's rule. I am determined to do it.
But this is already Hamilton.
It is, but I have to reveal it, right? I have to show there's still another assumption required. So the last assumption required, all right, the progress we've made. We've gotten up to this point where we have b times the regression. This is what you want to say. This is the coefficient from the best fit line relating your partner's genotype to yours. I'll say that again. This is the slope of the best fit line across a bunch of pairs, right? So you want to imagine finding a bunch of dyads in this population and genotyping them. And then you can make a scatter plot where one of the individual's genotypes is on one axis and the other's is on the other. Every point is a dyad. There's some best fit line that describes the predictive power of your genotype for the other individual's allele. And that's a slope. Yeah? Does this feel like data now? Feel like we made some progress? This is progress. Like this is wonderful. If you're a theoretical biologist and you get to an expression where you could plug data into it, that's victory, right? Clock out, go relax, right? and come back in the morning and find a bug. Yeah, but this is a lot of progress. But this isn't calculated from pedigrees yet, and we still need a justification for saying this is little r, which is this thing we usually talk about as the proportion of alleles which are identical by descent. That's this Sewell-Wright's coefficient of relationship, this little r thing. So let's think through a couple of examples, and I'm going to use those to pull your intuition into an expression for little r, if we think about it in terms of genotypes and relationship. But let's start by thinking about just some examples, because all of you know enough biology to think this through. What do we want? Well, we want an expression for this. right? This is the only thing we don't know in the expression in the bottom right. Every other term is done. But this is the one that is biologically active. So we must relate this somehow to Sewell-Wright's coefficient of relationship. And there are going to be two terms in this. Here's the way you want to think about it. So Sewell-Wright's coefficient of relationship, this is this little r thing, right, that goes back a long way. So Sewell-Wright used this mainly with guinea pigs. The biologists here who've been through classic lectures on this. Sewell-Wright's one of the fathers of population genetics, did a bunch of work on guinea pigs. He used to give lectures where he had guinea pigs running around on his table. There's this apocryphal story from one of his former students where he once erased the board with a guinea pig. I want that to be true, but there is no physical evidence right, that it really happened. But it's very plausible if you look at old photos of him in his lecture hall and stuff. They're guinea pigs and he loved them, just loved them. And he did a bunch of really foundational work in genetics by breeding guinea pigs and studying their coat patterns, and invented path analysis and a bunch of other important statistical techniques in the process. And one of the things he's known for is figuring out how you would calculate these probabilities of identity by descent. That is, the proportion of alleles that individuals share that they get from through descent, that are identical because they inherited them from common ancestors. That's what identical by descent means. And this little r, there are rules for calculating it from pedigrees. Your full siblings, it's a half. With your parents, it's a half. Yeah, with your cousins, it's a quarter, and so on. Yeah, those rules. Does it ring a bell? You remember how to do that stuff? Okay. So by that definition, there are going to be two terms in this. Boy, I'm really out of time. The first is all the alleles that, so individuals J and I. So your individual I, you're considering individual J's genotype at a particular locus. There are two ways you could have, you could both have the same alleles. The first is the proportion identical by descent, which is R, a proportion of your genome is identical by descent, which is the definition of Sewell-Wright's coefficient of relationship. Now among that portion of your genome which is identical by descent with individual J, what proportion are altruism alleles? This is a hard question, so the eyes to the ceiling are totally appropriate, but you can think through it in examples. Imagine you have no altruism alleles. Now you're contemplating in that proportion of the genome in individual J that's identical with yours by common descent, what proportion are altruism alleles? You have no altruism alleles. So what proportion in individual J are identical by descent? 0. Yeah? What if you only have altruism alleles at this locus? Then what proportion of alleles identical by descent in individual J are altruism alleles? 1, exactly. So I assert through hand-wavy applied mathematics that it is P sub I is the proportion of the alleles identical by descent that are also altruism alleles in individual J. It's just definition. Doesn't it feel wrong? But it's just definition. These are the definitions of these variables. Yeah, good times? Biology is going to reassert itself in the last minute I have here. The rest of the genome, 1 minus R of it, is just outbred. And so that's just P, right? Because you could both have altruism alleles just because the whole species has altruism alleles. That's the idea.
P is the general population.
It's the expectation of P sub I. Okay, I'm going to solve this for R. So R Pi minus P plus P equals the expectation of Pj Pi. So R equals the expectation of Pj conditional on Pi minus P over Pi minus P. And that looks familiar, I hope. This is this. Full circle. Now we have a way to calculate R from pedigrees. Does it feel good? We have reached the station. Okay, one last thing. Hidden assumption in this last step, and then we'll be done, was very, very weak selection. I said no selection when I did the outline, which is a bit cheeky of me. We want to take the limit as selection vanishes to 0, and we need to do that for this to be exactly true, because I snuck it past you when I asked you to imagine proportions of alleles on the pedigree. If selection is strong, such that there's some allele that never produces a viable adult, then obviously this changes the calculation. Well, it's not obvious at all, actually, so I shouldn't say that. It sneaks up on you. But if you're trying to predict your sibling's genotype, and there's some allele that's lethal, you know your sibling doesn't have it. Yeah? So all of these rules you're taught about calculating genotypes or overlap in genotypes from pedigrees assumes no selection. Because otherwise, there's biasing of the frequencies in every generation, and in order to do the calculations properly, you have to account for the selection coefficient. And we always ignore that because, well, no one says, but you can justify it for close relatives and weak selection. This is a fantastic approximation, because there aren't very many links in the pedigree by which the selection distortion happens, and if selection is weak, it's even smaller. And so this is a fine approximation for close relatives under weak selection. If you've got traits that are lethal or required for survival, then this is not a good approximation, and then you need to redo the model. You can still do a model, but you got to redo the model without this last step. Yeah, you're stuck with this regression definition, which there's a big literature out there of people who just use the regression definition with this.
I don't remember well how to gain a gene in mice, for example, right? But does it mean, I'm confused now, does it mean that this is a strong selection?
Yes, those scenarios, like the T allele in mice, that's strong. So I would say that's very strong selection.
So the T allele, you mean connected to the immune response?
No, I think it's called the T allele. This is the genetic drive thing. Anyway, it doesn't. Sorry. Let me summarize, and then we're like 4 minutes over, and I feel terrible about that. So I do. It's like stealing time from your lives. Where was I? Yeah, so you can work with this general regression definition and do lots of good biology, and there's a big literature of empirical papers that use this regression definition because they don't want to deal with this other stuff. And you can do lots of stuff with the regression definition. For example, relatedness can be negative because there's nothing stopping that expression from being negative. What would that mean? Your genotype anti-predicts the genotypes of individuals you interact with. And this happens routinely in nature because of dispersal. If relatives avoid one another when dispersing, then they will be on average negatively related to other group members. Does that blow your mind? Yeah.
Population level, you mean it's on average?
Yeah. So the individuals you're interacting with are less like you than the population mean, because your family members are out there. So the population mean is more similar to you because your family is in it, but you're not interacting with your family. And there are definitely social behaviors where you don't want to interact with your relatives. That's all I'll say. The holidays are coming up. Okay. Thank you all for your indulgence. I'm sorry I took 4 minutes of your extra time. Homework problem up, which I think you'll like. It's not as hard as the lecture. And last lecture on Wednesday, I'm going to continue from here, and we're going to think about the regression definition and add spatial structure to a population and think about what that does to assortment. Thank you very much, and I'll see you then.